Thank you very much. So I'm back. So this is part 2. So I told you yesterday was really basic, how to do one-by-one experiment. This part is more a series of examples. I hope I will kind of find something that all of you can find something that is related to this part of what we're doing. So quick recap from yesterday. This is what we want to do, right? We plant the Muon, we see how the lithium or whatever ion is moving, and we see this as a change, a dynamic change in the equilibrium function. It becomes more dynamic, when the answer becomes more dynamic. This was all our setup rules and tips. And then we basically do a temperature-dependent measurement of field fluctuation rate, or what we say ion hopping rate, and we can fit this in activation energies and so on. And if we know hopping paths and sound paths in your material, you can also calculate the diffusion coefficient on this. This was from yesterday. So I would like to, so yesterday I basically talked about lithium only. Of course, it doesn't limit to lithium, but for batteries, lithium is the most known type of battery. For lithium-ion batteries, this is what we use in all our devices and so on. Yet, as a small background, is that we use quite a lot of lithium. Already before we kind of had the real breakthrough electrical cars, 30% of all our lithium that we use is used for batteries. And there are some concerns about how this lithium is distributed in the world. You can find different types of plots like this. And depending on which politician has made it, because everyone wants to claim they have the biggest lithium resources, of course, it's very important. But it basically, a lot of it is in South Africa, which is great for South Africa. South America, sorry. So this is a bit of a concern. Also, it's kind of a nasty task to actually extract lithium. It's not very good for the environment and also for the people doing it. There are some other problems that lithium alloys with many metals. For instance, in batteries, you cannot use cheaper aluminum contacts. You have to use gold or copper. That's easy to do. Another thing is that the price of lithium has tripled the last 5 years. This I have to keep updating. This is already too old. It's probably 5 or 6 times the price now. So this is a really big thing. So you have something that is really not well distributed all over the world, so not everyone has access to it. It's quite nasty for the environment, and the price is going up very fast. This reminds you of something, right? This is basically the oil before. The question is, should we kind of try to find some sort of alternative? Maybe not a replacement, but if you find an alternative, at least you're not fully dependent on only the countries that are sitting on the resources, right? So one way to do is to take a step down. So you can go from lithium to sodium, for instance. There are other options. So I want to take the example of sodium just to show that you can also study sodium diffusion. So, from battery's point of view, so sodium is one of the most abundant elements in the world. So you have it in the Earth's crust, so it has about 1,000 times more abundant than lithium. This is great. Of course, you have it also in ocean, the water. It's accessible to everyone. This is great, of course. It's also one of the cheapest metals, which of course relates partly to this. You can use aluminum contacts. It's also good. So it's kind of a good idea to maybe have a look at this. And this is not something completely new. Sodium batteries has existed for a long time. Of course, sodium is bigger and heavier, so you can expect that this is more tricky to kind of move these ions around, of course. So maybe for for computer or your mobile phone, this is not the ideal case. But if you do this at home, for instance, and you want to have a battery in your basement or underground or something, you don't really care if it's much bigger and heavier, right? If it's much cheaper, then you do care. This is already kind of possible. So for decentralized energy production and smart grids, for instance, this is very interesting. So we decided to have a look on this. So yesterday I talked about lithium cobalt oxide. So we say, where should we start? We start with sodium cobalt oxide. Seems like a fair place to start. So this is exactly the same slide as I showed you before. I just replaced this part with data from sodium cobalt oxide. So this is what we did basically. We put our sample in this, we did temperature dependence, we fit this globally like some of you did yesterday during the exercise. And then we can extract the hopping rate as a function of temperature. This is exactly the same. So these pink dots here is actually the data that I showed you yesterday. This was lithium about 0.7 cobalt oxide. This was 145. The blue ones are sodium 0.7 cobalt oxide. So we try to make a fair comparison here. And as you might have expected, this diffusion starts much later. You have a much higher activation energy, about 3 times. This seems all fine, right? But if you ask Cedar, for instance, one of the famous guys calculating diffusion in materials, sodium and lithium cobalt oxide should be about the same activation energy. Actually, maybe the sodium should be even lower. So the question is why? He's very fair in his paper. He basically said that, okay, we don't really know the structures, we take the basic hexagonal structure that we assume for all these materials, and we plug it in, and then we calculate and we get this. Now, of course, your models are only as good as what you put in them. So if you have, let's say, the wrong structure, of course, what you get out will be wrong. This is quite natural. And this is a big lack, that we have very advanced calculation methods for molecular dynamics and so on and so forth. But we don't have many materials that they are applied to where you actually have all this high resolution data of structure even. And if you have it, most of the time you have it at room temperature. This is really kind of lack of things. And this is because, of course, you need to measure this at a large scale facility where you need to get beam time and so on and so forth. So we're lagging behind, so we need to do much more of this work. So actually what we did was that we put our sample in a neutron beam. This is a Muon spool, but I told you yesterday that complementary technique is very important. And if you don't know your Hawking paths, your calculation of the diffusion coefficient will be wrong. So we actually measure this. These are 2 diffraction peaks. This is temperature along the x-axis. We see that 1 peak or 2 peaks splits and change around room temperature. And then the second one, it splits again and goes back somehow, emerges again around 400 Kelvin. So room temperature 300 or 290 and 400. Yet, of course, you see this 300 here. This is kind of also where this starts to happen. This is already kind of an indication that something is connected. And what actually happens here is that if you look in the sodium layers, this sodium sits in 2 different sites, sodium 1 and 2, in this type of triangle with 1 in the center. And at the low temperature, we have a monoclinic setting, so this is distorted. So everything is completely distorted, and you have 3 different lengths here, short, medium, and long. And then in the middle here, you have orthorhombic, so slightly more symmetric, with 2 short, 1 long. And then above, you have truly the hexagonal one, finally, where everything is symmetric and nice. And I should just keep that one. So what you can do with very high resolution, high statistic neutron or X-ray diffraction data is that you can do so-called Fourier analysis. So you do a Fourier difference map. This is basically somehow a difference between your data and your fit, that is your static model. And this, of course, your fit needs to be correct as possible. And then you make a difference and transform this into Fourier space, by Fourier transformation into real space from field space. And then you get these maps. So this is a slice in the sodium plane, and blue here means minimum. So this basically means that everything is static, everything is well described by your model. So you have no difference. And these small dots here, these are the sites for the sodium, so it's all blue. Then when you pass the first transition around room temperature, you get this intensity that you see as red and turquoise here. So this means that somehow between sodium 1 and sodium 2 there is an intensity in real space. Yeah? And what's interesting is you only see this high intensity where you have the short distance. You see a little bit, but not so much where you have the long distance. So this means basically that you have some sort of jump paths opening up in one quasi 1D direction like this, only where you have this short distance. And this structural transition, if you go back here, to this one, you will see that this is the lattice parameters. And what they change is from 2.835 angstrom to 2.840. This is 0.005 angstrom difference in your lattice. This is all it takes for this diffusion path to open. So it can be a very big difference. I mean, of course, if you just have these small changes in your material. And then above, where all this is equal, you open the second till you get this fully 2D diffusion in the plane. This is clear. It's not like this at room temperature. It's like this. This makes a difference, of course, when you put it in your model and how you calculate things. And just to kind of prove, we also use so-called quasi-elastic neutron scattering. So this is an energy result. So you can actually look at dynamics with neutrons as well. And what we see is actually that the static intensity of the material goes down around the first transition, and the inelastic goes up, and in 2 steps, at T1 and T2. And that the inelastic goes up means that the dynamics is increasing in 2 steps. These are probably related to these two, 1D versus 2D diffusion. This is kind of, I would say, bulletproof that we now know what we're looking at. It's also very nicely confirmed that what we're actually looking at with muons is not muon diffusion. There are no muons in here, and even if they were, we wouldn't see them with neutrons. You know. So, simple is that we have our jump paths. So, low temperature, we only have the pink ones. And we can calculate diffusion coefficient. At high temperature, we have all of these. You can plug it in and we can calculate. So this is how you should do if you do everything properly. Of course, this is several years of work. Right? Don't do this in an afternoon. But this is what we need to do. And we need to supply this high resolution type of data to people that model. We need to do this. We can't do this for all materials, but we can do it for groups of materials that you can consider having the same type of properties. This is very important. So, next one. So, I showed you that we can look at sodium. You can actually also look at potassium. Just to tell you, we have done this. This works. I have seen some work on magnesium also. It's more tricky because there you have to keep an eye on your isotopes. I think the magnesium, if I remember, there is only like 10% the natural abundance that has a moment. It's more tricky. So this is what you kind of have to keep an eye out. But hydrogen storage. So we talked about fuel cells. I mentioned this, that this is half of the picture I showed you yesterday. And this is all fine, but you need some sort of fuel for it, right? So hydrogen is one of the more common things. Of course, you can have a hydrogen bottle. This is a very primitive form of hydrogen storage. This is a little bit more kind of the future, maybe. So this is a drive to go to all solid states. You take the material, you push in hydrogen in this, and this is your hydrogen storage basically. And this has many advantages, this solid state. This is one, that it's a bit safer, because people are really uncomfortable driving around with this type of gas bottle in the car, even though no one ever thinks about they have a gasoline in the car. This is apparently fine. It's also explosive. Just as a sidetrack, I mean, everyone is so worried about the electrical car now, so that they are so unsafe and so on. And sometimes you see an electrical car on the news, Tesla that is burning somewhere, but there are many, many of these normal cars that also catch fire every year, right? So no one ever talks about it. I think it's about 200,000 per year in the US or something. So this is the Hindenburg disaster, very terrible, of course. But the solid state solutions are, of course, much less volatile. Even though it wouldn't be very great to have this part in solid state, that wouldn't work either. Another thing that people not working in the field or being scientists doesn't know is that actually the volumetric storage capacity is better in solid state. And then you're having gases or liquid hydrogen. So if you have a high pressure gas, you have some hydrogen, you can actually store much more in solid state. So this is of course much favorable as well. But the name of the game is the same as for batteries basically. That solid state means difficult to transport ions, in this case hydrogen. So the operation temperature is too high, so we need to do material science and improve this. We can do this much more efficiently at low temperature. So this is really the name of the game also here. Just all the same. So complex hydrides is heavily regulated for being such materials. Major problem, as I say, the desorption temperature is quite high. So there is clearly a lack of experimental methods to study this, really material properties, as I said before. And we did some study on a range of these materials by Muon, metal borohydride. And one of the bases for this is that we probably talked about the FMF on during this, you know what it is, but so you have this nice oscillation that you get. FMUF is the classic one, but of course it doesn't need to be F. We tend to call them FMUF no matter what sits here. So there are many possibilities, but in the complex metal borohydride, hydrogen actually has a valence of -1, and this is something that I was a bit surprised before I understood what we were looking at. So there is a possibility that we can get this type of H-mu-H bond. And this is what we have actually. So this is sodium borohydride. So here, very nice oscillation at low temperature that gradually breaks up when you go around room temperature. This weak bond is breaking up. And you also see that the symmetry of this oscillation from this H-mu-H change with different materials. So here it's much clearer, then it gets weaker and weaker, and it's almost you can see it here. And actually, if you plot this asymmetry as a function of the desorption temperature, you have a linear dependence. This is very interesting. So when we published this back in the days, it was basically to say that, okay, it seems like a quick way to kind of determine TB and somehow determine the dynamic stability of these materials by Muon. Because basically you just need to cool it back to low temperature and measure one. And you can, so this will be, let's say, a way to look at this material. Of course, you can move forward. So another material, magnesium hydride, is considered one of the promising materials. All materials are promising, at least the one one. But the pristine material has quite a high desorption temperature. So this is the temperature program desorption. So you see, this is as prepared material, so about 700 K, something like this. But if you mill this, so you basically make the grains smaller, I guess. You can lower this down to with about 100 K. So this is quite easy to understand that if you have the smaller particles, it's easy for the hydrogen to move out. This I personally don't have seen a viable explanation, but if you mill it together with 5 or 8% of niobium oxide, you actually lower it another almost 100 K. This is very interesting. So you can have a look at this in the same way. So we see a very clear H-mu-H signal at low temperature. You can also see that as prepared, milled with this niobium oxide, you can see that this oscillation becomes clearer as we expect, right? So, and what we also see is that if you take, this is the milled one, so this is this one. If you go up in temperature, you see that at some point this breaks up around room temperature and you get the cool Teabe, that then becomes more and more dynamic when you go up in temperature. This is some sort of dynamics going on in this. So we can do this type of measurements. You can, first, you recognize all this by now. These are the different materials on different temperatures, but you clearly see at the same temperature it becomes more and more dynamic with the milled and the milled with the niobium oxide. And also, if you plot the hopping rate here, you see that one is flat up to here, one starts to kind of go up, and the red one milled with niobium clearly goes up here. You also see that you have a drastic change in delta here that follows all this. This is quite nice. I said something about in situ yesterday. So this is quite nice if you can do this. So basically there was a cell that was developed. So you see there, in the one I had yesterday was 1 gold gas, and this one has 2 for extra safety, yes. And also this is stainless steel because, yes, I told someone yesterday, but if you want to do these kind of things here at ISIS, at least, you're not allowed to do this in titanium for safety purposes. You have to do this in stainless. So basically you put your material here, you have these tracks here that goes into a channel that you can take the gas out to a gas line. So here is the muon coming in. This is your sample tube or furnace. You heat it here, and then when the hydrogen desorbs, it goes through this goes in here into the tank, and you can measure the pressure as you raise the temperature. So this is really neat. So you can, of course, you can reproduce the results just low temperature, you see everything is okay. We find that, okay, in the, I think the original paper, there is only one photodiode, I think. But you can actually fit it better if you add 2 photodiodes. Of course, it will fit even better with 5. But there is a reason for this. So this can be seen as both a bulk surface contribution. So this is something if you start looking, if you're working with nanoparticles, for instance, where the surface starts to become more and more important, you have to start thinking about these kind of things when you fit your data. So just a tip. Also, muon site DT calculation actually show that there is likely that the muons, you don't have one local minima, you have like a cube. So it could be that the muons themselves are actually delocalized along this one tube. So that makes things, of course, even more complicated, right? And more contributions in there. So I will not go into details because, but I can just show you that this is the pressure. This is the as prepared, milled, and milled with niobium material. You can see that this when you go up in temperature, this pressure in the tank goes up, but the temperature it just goes down. This is also strongly correlated with what we see in the heat fluctuation rate and also the change here in delta. So this is very complicated because we have these possibly delocalized muons, right? And then we have some sort of dynamics that is probably related to the hydrogen. And at the same time, when this drop here, because what actually happens when hydrogen dissolves is that the material basically change. Okay. So you have some sort of structural change. This is even more complicated. So what are we actually looking at? This is the question. And if this is actually hydrogen or muons or both, I will be a teaser because I think June will probably talk a little bit about this. No? Okay, too bad. We have to ask us after. But anyway, so I think it's clear that at least hydrogen is coming out. This is kind of a confirmation here. This is so hydrogen storage. Sodium batteries, potassium batteries, magnesium batteries, whatever you want. Nuclear waste management by Muon. Sounds like a contradiction somewhere. But everyone knows that we have nuclear power plants where we have used fuel, active waste. There's about 50,000 tons of nuclear waste, at least in 2002. I couldn't find any more recent numbers. No one wants to show these statistics in the US, for instance. And the fantastic solution to this is that we dig a big hole and we hide it here and we don't think about it. This is the kind of ingenious solution that many came up with. So we need to do this. The question is this type of deep geological repository is 500 meters down. We need to store this for, I say 100 years or more, but it's much more than this. But the 100 years is basically what we can consider what happens to our containment. So it's basically they say 100 years because I come up with this and then 100 years has passed, I'm gone. So this is kind of, I think, why we push 100 years. So this, of course, puts some extreme constraints on materials. So you need to dig it down and so on, and you need to encapsulate these active isotopes, and you don't want them to get out in the groundwater and stuff like this. And there are several suggestions to make this out of copper, stainless steel, concrete, and so on. But then what many agree is that they should somehow encapsulate them on top of this in some sort of synthetic clays, so mud. And this is both sealing and some sort of buffer layer. If something starts to leak, they should kind of only be taken care of by this, some sort of filter almost. And of course, then understanding diffusion of these active isotopes in these clays is very important. This is very, very complex because it also involves water diffusion as well as dynamics of the active isotope, but also many of these clays have lithium and sodium in them, by chance. So clays, one of the main components depending on the clay, of course, is in bentonite clays is the morillonite. And in its dry state, it's very similar to battery material actually. So it has some sort of metal oxide sheets, and then you have water with cations in here. And when you hydrate, then water goes in, and then this expands in this direction. But the main idea is that to study this, we cannot, again, use only one technique. But in the dry state, we can study sodium-lithium diffusion very easily. This is very ideal. And then in the hydrated state, this is much more complicated with muons, but it has a very high scattering from neutrons. So basically the idea was that we start by looking at dry samples with muons, and then we go on the hydrogen materials with neutrons. And the combination of these two techniques should give a good view of this. So to start recognizing this guy now. So we say, okay, what should we do? We take a sample, we dry it, we seal it in the glove box and everything with a thin micro window. And we started looking at natural and synthetic molten rhyolite. But we got some problems because we have really strong exponentially relaxing signal. We couldn't figure out why. So this was, and then we realized that there was really a lot of just iron inside the sample. So this was complicating our life a lot. This was just a small piece of information that was missing from our sample. We say, okay, what should we do? We only had one lead time left. So we focused on something else, on a hectorite clay, synthetic one that was better controlled. So we found a good protocol where we really dry it and pack it immediately after we dry it. Because even within 10 minutes it starts to suck up moisture from the air. And also what's great is that if you look here, there is no iron in the area. So this made it nice. We could actually get, the fit here is not great, but this is work in progress. But what is clear is that you can see that this goes dynamic with higher temperatures. We actually can see that already around 150 K, you start getting increase on this. You can extract some sort of activation, and we need a lot more work on this. But at least this is the first observation of this type of materials, at least what I can find. So this is interesting. I think solving the nuclear waste management by MUX is probably a nice title for a funding proposal or something. I believe. So this is Anne Jurani at Porsche Institute in Switzerland. So she's the lead of this proposal. She didn't do muons before. But we want to produce this synthetic clays with a better protocol to reduce the presence of iron. Of course, the packing protocol and everything, we need to probably dry them inside the glove box and stuff like this. So we need a dedicated glove box for this. And then, of course, we should combine them with cleanse. This has actually started now. So, I have plenty. So, summary of, let's say, what I've shown you so far would be that I think MUSAR is a very good experimental method to study ion dynamics. It's not always straightforward to analyze and understand the results, of course. You have to remember that you measure in field fluctuation rate. This is really our distribution. That might be your ion configuration. This is just to remember this. Complementary techniques, I think I pushed this quite hard at, for instance, neutron diffraction or synchrotron or whatever, are really favorable, for instance, for taking the diffusion pathways. Select your sample carefully, nuclear magnetic moment, blah, blah. Also check them, talk to your sample provider before you waste muon lead, like I did. Do your homework. So what can you expect about stable muons or not stable muons and stuff like this. So if go for dynamic, it's of course not impossible, and sometimes you can even use the muon being dynamic in your system as a model. Be systematic. I think this is really because this is not something I should say for making an article, but at least during experiments, if you're very systematic and you fit your data, even if the fit is not the absolute best ever fit that you want to put in your paper, if you do it systematically and do it properly, you will still manage to see changes, right? It might not be the ultimate absolute numbers and so on, but you will be able to see where it goes and where you want to go. So this is, and if you're systematic in your actual experiment and how you do your measurement, you at least remove this part of the changes, right? So this is really important. If you want to do this, I wish you good luck. And of course, if you want some help or advice, you can always contact me. You have my name. If you Google me, you will find it without problems. So, acknowledgement. There are many people involved in all I show you now. I show you the key persons. Young obviously is here. You'll see him today. Give me a lecture. Izumi Mugaki in Toyota right now. She did a lot of work on the hydrogen stuff. Marisa Medarde for all our neutron diffraction work. She was really invaluable to this. She's, I think her PhD supervisor wrote the full prof, basically Swede, so she knows what to do with diffraction. Yasmin Sasa joined all the experiments that I think almost showed them on the hydrogen. And then, of course, so my own team, SMART. So Ula is here, looks slightly different today. And Elisabetta, both my students and my postdoc, and of course, we can't do anything without all the people in all the sources we have used for it. So no one mentioned all of them. So, with that, this is the end of part 2. But, you do me a favor.